All right, I know we did this yesterday. If you did not write this down yesterday, I want you to write it down again. I want you to write it today. All right. So above that picture, this is what I want you to write. Yes, please. Above that picture that I just showed you. All right. The reason I'm doing this again is because I want to say it one more time to make sure everybody's on the same page, and there was like 8 of y'all missing yesterday as well. So, again, one more time real quick. I promise I'll come back to this. Above this slide, it's on the back of the very front page. Above this slide, that's what I need you to write down. Wherever you wrote it, as long as you wrote it. All right, so this is what it says. Now, obviously what this is referring to, and we'll talk about it in just a second, so when I go back to the other page, this is referring to the atomic radius. This is what it says. The atomic radius is half the distance between the nuclei of two identical atoms that are bonded together. Anybody else still writing? Okay. Half the distance between the nuclei of two identical atoms bonded together. Like I said, I know I said this yesterday, but I'm hitting the high point one more time. Anybody else need another second? So let's look at this picture again. So first of all, what two things are those circles representing? Are they identical? Are they bonded together? Yes. That black line that's connecting the two centers. What are the two centers of an atom? The nucleus. Very good. So again, it's the nucleus. Okay. And half of that line is called the atomic radius. Okay. So the definition matches the picture. Okay? And the reason why we said this is how they do it is because yesterday I showed you this picture, and that very first bullet talks about the radius of an atom is the distance from the center of the nucleus to the outer portion of the electron cloud. And what do we say about clouds? You don't know where they end, right? They're always changing shapes. Like you don't know what a cloud looks like because it's always changing. And so that's why they do it that way. All right, did I draw anything on this? All right, so here's what I want you to do. This is the exact same picture. Did I do anything on the last slide either? Okay, very good. I want to say it again just for everybody else. As you move left to right, what happens to the size of every atom? Smaller, if you want to write that down. So left to right, they get smaller. And what happens when you go from top to bottom? They get bigger. That's just a miniature fact just to kind of make sure you understand. All right, the thing that I want to point out on this is take your pencil and try your best to circle all of these peaks and all of those elements. Okay? There's something that all of those elements on top and that are listed have in common. Can anyone tell me what they all have in common? You are absolutely correct. Be a little more general. Perfect. That's what I was looking for. These are all group 1 elements. All, 7 of those? 1, 2, 3, no, all 6 of them. Okay. All right. Then, take your pencil, not excluding hydrogen, just fluorine, chlorine, bromine, iodine, and I know polonium really doesn't belong here. So polonium is really an exception too. Can anyone tell me what the bottom ones have a common theme of? Except, again, like I said, except polonium. So these 4 right here. Very good. I guess because they're representing groups. Oh, no, I had no idea. I have no idea. Anybody tell me what group got left off? Noble gases. What group number is that? 18. If you look back there on that one, the one hanging to your right in the middle back there, that far, far, far right column, what do you notice about the size of those spheres as compared to the rest of them? They're all smaller. So if we had to plot the points of all the group 18s, would they be above group 1 or below group 17? They'd be below because they're smaller. Does that kind of make sense? Again, I just wanted you to make sure that you could kind of see a common theme with that. All right. So let's talk about things we already know. I think you would agree this is a fact that you already know. Atoms of different elements have different number of protons. Does that make sense? Okay. Atoms of the same element have the same number of protons. That makes sense. Now, let me kind of tell you something that will just make you frustrated. Whenever I ask about the letter F in temperature, what does that stand for? Fahrenheit, okay? What does the letter L in volume stand for? Liters. Here's a tricky one. What does the lowercase letter Q stand for? Not the unit. What does it stand for? Energy transferred, right? Okay. What does the letter H stand for? What is enthalpy? See, I told you you'd all remember. Now, yeah, for some strange, odd reason, the people who designed this next letter are crazy. They chose the letter Z to represent what thing? Yes, absolutely. The atomic number. Why in the world would they choose Z to represent the atomic number? I don't know that, but it need to be beaten with a stick. Again, if you think it's awesome, congratulations. I don't understand the reason for it. However, sometimes life is what it is, and we don't understand certain things about it. And this is one of the ones that just doesn't make sense. So I just need you to know that fact. I'm begging you, please, please, please. So if I ask you this question, what element has a Z of 6? Carbon. So while you would look up there and you would find number 6. So, but if I say Z, you're going to look at me and say, I don't know what you're talking about. But what does the letter Z represent? Atomic number. Again, please know that. And this is the second thing I make sure you know. What does the atomic number actually tell you about that element? Number of protons. Please, please, please make sure you understand that. I cannot stress to you how important that is. The atomic number, the symbol, for some odd reason, is Z, and it tells you the number of protons. Okay? So I know you don't have this slide, but this is just a basic generic picture. So all those whole numbers up there, those are all the atomic number, and they represent the number of protons. Okay? Now, we've already discussed everything that's on this slide. Some of you wrote it down, some of you didn't. So what I did is I said, if they're not going to write it down, I'm going to put it in notes form, so the second time you see it, if you've already written, that's good. But this is in here, so when you're reading through these, it's kind of help you out. Isotopes are atom of the what? This is important. Same element that have a different mass. That's a fact my 8-year-old niece can memorize, and I told you that yesterday. Why do they have different masses? Perfect. That's what's right there in big, bold, and blue. So if you want to highlight or circle that, that's fine. Okay. So, same element always has the same number of protons. But if you change the neutrons, what do we call that thing? An isotope. Very good. That's what it's called. So again, same element, different masses, because they have a different number of neutrons. Now again, almost everything on the entire face of the planet has different isotopes. So every element has multiple isotopes. All right. Another fact. Put a big, huge star or circle around this slide together. And there's two things we're going to add to it. Okay? Two things. Remember a second ago that I told you the letter Z represented what? Atomic number. This one's going to make just as little sense. The letter that represents the mass number is the letter A. To me, it'd make a whole lot more sense for A to be the atomic number, but they thought otherwise. All right, does that make sense? Okay. Again, it's a weird, odd fact you just kind of got to apply it with. So instead of writing the word mass number, you can just write the letter what? A. Just like instead of writing that whole big, ugly word Fahrenheit, you can write F. Okay, same concept, just doesn't make sense. So what is the mass number? It's the total number of what plus what? Protons plus neutrons. So another way you could say it is A is equal to P positive plus N, and that's called the naught symbol, N-A-U-G-H-T. So A is equal to P positive plus N naught. One more thing that I want to talk about. Is it possible for an atom to have half a proton? No, can't be halves. Can't be quarters, can't be anything decimal. Is it possible for an atom to have half a neutron? No, it's impossible. So here's a question. If you can't have any halves or decimals or anything like that, when you add these two numbers together, what should your answer always be in? Perfect. Write that down. Okay. So the mass number is always a whole number. So let me ask you this final follow-up question. And this is the part where I'm seeing if you can think. And I'm going to answer this later. I'm not going to just leave you hanging. We'll talk about it later, but I want to propose the question now. If I ask you to find the mass of any element on the periodic table, how does that number compare to what we just said? All of those numbers are in what form? The masses. They're decimals. So how can we go from whole numbers to up here, they're decimals? Not necessarily, because you can't have half of anything. Fabiana, you got an answer? Anybody got anything for a reason why? Let me give you a hint. It has to do with an average. What do you think it has to do with an average of? That I where we keep talking about isotopes. And again, it has to do with the average of isotopes, and we'll talk about that a little bit later on. So just kind of keep that back there. The reason it's decimals is it's an average of something. Okay. Again, we don't have this picture, but the way they get. So what is 8 plus 8? So the mass number of that atom would be 16. But on the periodic table, it says the mass is 15.994. Again, that doesn't make sense, but we just said that that number is what? An average of all the isotopes, and we'll talk about that. Okay? Both of these are TQs. What do I mean by TQs? Test questions. These two right here are test questions. One of them is really, really easy. How do you know that that top thing is written in hyphen notation? Oh my gosh, you're so smart. All right, but here's the problem. And every year, people miss this question for the following reason. Obviously, there's a hyphen. That makes sense. But the number. What is the value equivalent to? Mass number. Okay? Here's what I don't want you to do. First of all, does anybody know what number uranium is up there? 92. I don't want you to say it's the atomic number. Because I'm telling you, on the test, you're going to see one just like this, and it's going to say uranium-92. And that makes sense because uranium is 92, but hyphen notation is the hyphen and the what behind it? Mass number, okay? I'm just telling you that's where people get confused. So hyphen notation is the hyphen and the mass number. All right, the nuclear symbol. This one's the one that kind of gets a few people. Let me give you something really simple to help to hang on to here. Write it kind of like this. The nuclear symbol is always the bigger number on top of the smaller number. It's always like that. So if you ever have to write it, make sure you write the bigger number on top. Do you agree if that was an addition or subtraction to make it a whole lot easier? Okay, think about it from that perspective, because in fact we are going to do a smidge of math with it. So the superscript is the mass number, where the subscript is the atomic number. And there's one last thing I want you to write beside this. And we've just talked about two of these letters. Does anyone remember what the A stood for? Very good. Mass number. Does anyone remember what the Z stood for? Atomic number. And the interesting question, what in the world is X? Very good, look at you. What is the name of element X? Very good, it was a trick question. There is no such element as X. Here's a question. This is one of those I can stump your friends kind of questions. Don't answer it out loud. Think for it. Give everyone a chance, because someone may already know this. There's only one letter in the entire alphabet that is not present on the periodic table. Just one of the 26. Does anyone already know what it is? Okay. No, you don't get to say. Okay. It's not Q. Q is up there. Everybody always says Q and Z, but Q and Z are up there. Alright, what is it? It is not Y, because Y is up there several times. Yttrium, urbidium. Number 39. What you got? It is not X, because xenon is Xe. K, do you know already? It is J. Very good. J is the only letter. Do you know that? Okay. J is the only letter. Just again, one of those fun, interesting facts that's not present on the periodic table. That they've never chosen J to be an element. In fact, I can't even think of an element that the name has a J anywhere in it. Well, that's true. That is very true. But I'm talking about like the name itself. But you're right. I don't know if any of the new ones, like, they just discovered some of the new ones. I don't know if any of those are going to have J. Yeah. Remember when y'all colored that periodic table, I told you there was some new ones that they just showed up? Hold on. Let me pause this. All right. That's right. It. Yeah, un quadium. The reason, and this will make sense. Un means one. No, it's un nil quadium. Un is one. Nil is 0. Quad is 4. 104. So it's number 104. Like, un quadium. So 114. Un nil quadium and un quadium. Okay. See, I knew I wasn't crazy. And the reason why is because that periodic table doesn't have any of the Q's for the 104 and 114. So now Q is officially left off the periodic table. Interesting fact for the day. You have hope. You have hope. So here's the basic math that I want you guys to be able to do. Simple basic math. The number of neutrons is found by subtracting the atomic number from the mass number. Okay, well, think about this. What is the mass number made up of? We've already talked about it. Protons and neutrons. Okay? What is the atomic number made up of? Protons. Well, if one is protons and neutrons, and one is just protons, can I just do a basic subtraction and find the number of neutrons? Okay, that's all you would have to do. The interesting thing that I want to point out on this slide is one thing, and you're going to see this theme a lot, and you're going to hear me say it a lot. How many protons are in uranium? 92. In this isotope of uranium, how many neutrons did you find? 104. Does that look odd to you? 143 is kind of a lot, right? Compared to 92. In basic understanding, if I just talked about protons and neutrons in an atom, what would you expect them to be comparatively? The same. You would expect, so if you've got 92 protons, you would expect them to have what? 92 neutrons. Here's the fact of the day. That is more common than them being equal. Most of the time when we do this, and you're going to see this in just a few seconds, it's true that most atoms have more neutrons than they do protons. Now, I always get asked this question, well, why is that true? That's what Teddy and Noah are going to find out, because we don't know. That's your charge in life. You've now been charged with Teddy. You have to find out why. Okay? No, it's a joke. Like the physics and chemical communities do not understand why they're not equal. They've never figured out why some atoms have more than the others and why it has so many specifically. It's just the way the world was designed. But they don't understand why it was designed that way. What's the purpose of them acting that way? They really don't know. Okay, so that's kind of one of the interesting concepts. I know you don't have this slide, but I just kind of want to talk about it. So you just drew this right here. Okay, we said the mass number over the atomic number. So if I asked you about carbon 12, which is what it says, carbon dash 12. So the mass number is 12, the atomic number is 6. So for carbon 12, how many neutrons would it have? 6. 12 minus 6 is 6. And again, that's rare that they're the same. What about carbon 14? How many protons would it have? Protons. The way you know that's because it's the atomic number, right? But how many neutrons would you have? 8. 14 minus 6 is 8. Okay. Because 14 is the atomic number. Excuse me, mass number. 6 is the atomic number. So 8 plus 6 is 14, which is where the mass number comes from. So I have one little problem. Hang on real quick. I want to do something. This right here is the last thing we're going to do today. If you all get it right, we're done. You've got to all get it right. So, here's the question. How many protons, electrons, and neutrons are there in one atom of chlorine 37? And no cheating. So I need to know the number of protons, the number of neutrons, and the number of electrons in chlorine 37. So use all the notes that we just did and see if you can figure that out. Okay, there's more than one way to look at this, but I'm going to approach it from my perspective of how I would look at it. And so we want to know how many protons, electrons, and neutrons there are in chlorine 37. The first thing I'm going to look at is I'm going to look at what is my element. Okay, so up here on the wall, chlorine is what number? Now that number refers to what does it refer to specifically? That's the atomic number. And the atomic number is what by definition? All right, so I can go ahead and I know for a fact that the number of protons is 17 because that's the number that chlorine is. It's the atomic number. Now, this number right here, this is the part where people get confused. I've seen people in the past write that is 37 protons because they think that's the atomic number, but it's not. Number 37 is what? The mass number, which is equal to what? Protons plus neutrons. Now, so let's think about it logically. If I have the mass number, which is protons plus neutrons, I know it's 37. And I know I have my number of protons, I can just do a simple subtraction, right? So my mass number is 37, which again, what letter represents the mass number? A, very good. What letter represents the atomic number? Z. So it's really A minus Z, okay? And we know that that is 17, so what is your number of neutrons? 20, very good. And then the last perspective we need to look at is, if this atom is neutral, what two things determine neutrality? Very good. The positives and the negatives, the protons and the neutrons, protons and electrons. So if you've got 17 protons, 17 positives, how many negatives do you need to make it neutral? 17. So how many electrons do you got? Very good. And that should be your answer. Does that make sense? Very good. We will shut it down for the day.